You're late? Just kidding. Welcome to Lab O2B, determining the index of refraction of light. The purpose of this lab will be to determine the index of refraction for a piece of clear glass. So, let's get introduced to the apparatus. First, we'd better wash my hand. Polarizer, focusing lens, laser, optical rail. The glass is fastened on the angular translator perpendicular to the incoming ray of light so that no refraction of the light beam occurs. The material is then rotated to different angles on the angular translator and the light is refracted within the material. Each degree is split up into 60 parts, each part being 1/60th of a degree. These parts are called minutes and are the numbers listed on the bottom half of the angular translator. A photometer mounted on a linear translator, which is connected to the Data Studio software on the computer, is set at the opposite end of the optical rail. The sensor measures the relative intensity of the light beam. This linear translator is constructed with a non-digital micrometer, which is used to measure the position of the laser light beam. The Data Studio software is necessary to read the relative light intensity of the refracted laser light ray. By moving the linear translator's position, it moves the photometer back and forth through the refracted light. On the screen there is an arrow which moves from left to right from 0 to 100 in increments of 1. Adjust the linear translator while watching the computer screen. Try to get the arrow to the point where it won't go any higher and instead will turn around and start to go back down towards 0. This position should be between 40 and 90. If it is too high, the risk is run of the photosensor becoming oversaturated. If it is too low, then there is the chance that the reading will not be strong enough to accurately register on the photometer. If either extreme condition occurs, then the aperture opening in the front of the photometer may need adjustment. The silver arm extending from the aperture requires only very small movement when making this adjustment. Once the location is found where the percentage reading is at its actual maximum, then this represents the strongest, most intense point of light in the refracted laser beam. By reading this position, where the light intensity is at its maximum, it's possible to determine the position of the refracted laser light as it exits the glass block. Check all components for correct initial positions and alignment along the optics rail. Position the angular translator to read exactly 0 degrees to the minute of arc. If necessary, adjust the angular position of the glass on the angular translator so the laser reflection from its front surface is directed exactly back to the laser. Now adjust the linear translator, which moves the photometer's pickup to locate the position where the light intensity indicated on the computer is a maximum. Read and record this position as the 0 degree position. Adjust the angular translator to read exactly 20 degrees to the minute of arc. Again, adjust the linear translator to locate the position where the light intensity indicated on the computer is a maximum. Read and record this position as the 20 degree position. Continue repeating these steps 5 and 6 for 11 trials with incidence angles from 20 degrees to 70 degrees using 5-degree increments. Also, remember the optics room is small, so please keep your book bags in the seminar room. The purpose of this lab is to determine the index of refraction for a piece of clear glass. C is the speed of light in a vacuum. V is the speed of light in the medium. The index of refraction, N, is defined by the ratio of the light speed in a vacuum to the light speed in the medium. The index of refraction will be found by measuring the displacement caused in the laser light as the glass is rotated to different angles. From the original angles of incidence and the distance the laser light is displaced, it is possible to determine the angles of refraction using geometry. With these two angles, it is a simple process to determine the index of refraction by using Snell's law.